this story of World Academy and Human Security, it goes back all the way to Russell Einstein Manifesto. That was 70 years ago, and that's actually the start of the World Academy. And this was also
Yes.
very beautifully summarized. Last year, our friend Ivo Schlaus, the honorary president, he actually made a passionate plea, stop all wars now, because it's really dangerous. I mean, nuclear weapons, artificial intelligence, and many things that could go wrong. So it's really important that this stops. And of course, our president, Gary Jacobs, he also had a very successful project on human security for all with United Nations. So this concept is kind of gaining traction also in international organizations. And then also our Vice President,
Yes.
Donato Kinigar-Pastiglie, he has this vision of global peace offensive, which has been accepted also by European Academy of Art and Science, by Alma Mater European University in Maribor, and by many other organizations. And now there is some activity with Club of Rome, also Donato and the Secretary General of Club of Rome and the presidents are all involved. And I believe we are going to make massive progress. But also, I mean, we all know that these challenges are so great, and that in spite of everything we do, the wars are not stopping, they're getting worse, and there is all sorts of troubles all over the world. So that means we need
Yes.
new innovative approaches on what to do. And that's why I believe we also have a couple of ambassadors today with us. So we have people from different disciplines, from physics, from computer science, ambassadors from humanities. And all of us are going to be looking forward to listening first to these two introductions of our very special guests. They are both great people, great persons. And I think we just go right in medias res. Our first guest is Professor Sabu Thomas, the previous, just a few years ago, Vice Chancellor of Mahatma Gandhi University in Kottayam, Kerala. And Professor Sabu is not only one of the best in the world in nanotechnology, like with triple-digit Hirsch index, but also an outstanding educator. His students who are striving for knowledge, they really come at the right place, because once they meet his passion for teaching, they are hungry no more. And without a further delay, I would like to ask Professor Sabu Thomas to share in the next half an hour your view on nanotechnologies and how it can contribute to human security. And you are very welcome to share also the screen with your PowerPoint.
Very good evening. Thank you, Aleksander.
Thank you, sir.
Yeah, for your kind words. I'm really delighted to give a talk at the WAAS. My talk is centered around nanotechnologies for human security. Dear colleagues, I have two affiliations. One is Mahatma Gandhi University, where I started my career. I'm also the chairman of the Science Park, where we connect academy of the industry. Dear colleagues, friends, the science and engineering of nanoscale materials are getting a lot of momentum. And if you look at nanomaterials, the definition is they should have at least in one dimension, 1 to 100 nanometer size, at least in one dimension. Dear colleagues, nanomaterials play a very vital role in a variety of fields in medicine, electronics, energy, environment, material science. And nanomaterials have unusual properties, unusual physical properties, chemical properties, biological properties because of quantum confinements. And nanomaterials are quite important for a variety of applications, for safeguarding our ecosystem. We call it environmental security, health security, economic security, personal security. So nanomaterials should be utilized for combating diseases. Nanomaterials should be utilized for alleviating poverty. Nanomaterials should be utilized for solving environmental problems. Nanomaterials should be used to avoid violence and terrorism. And today, dear colleagues, I'm going to talk about how nanotechnology could be utilized for environmental security, particularly for clean water. That's the title of my talk. How nanostructured materials could be utilized for water security. My research group is quite active in this area. Coming to water, we all know the famous quote, water, water everywhere, but nary a drop to drink. If you look at the whole water in the earth, 75% of the earth's surface is covered in water. But dear colleagues, 97.5 parts of this water is salt water, leaving only 2.5% of water as fresh water. And if you look at the fresh water, nearly 70% of fresh water is frozen. And if you go down, what is really happening? Less than 1% of the world's fresh water is available to mankind. Therefore, it's very important that we should preserve our lake. We should preserve our water bodies. Let me also show you the water scarcity in 2025, the running year. If you look at India, India has tremendous water stress regions. You see, look at this is India. Water stress and water scarcity countries of 2025. India is going to face lots of problems with water. Again, if you look at water stressed and water scarce countries in 2000, you can see this sort of color. And no stress region, only very few parts of the world have very no stress. Let me also show you a statistics. In 2000, the relative sufficiency of water was 92% in 2000. And stress region was only 5%. And scarcity was only 3%. And today, 2025, look at the relative sufficiency. Relative sufficiency. 92% became 62%. There's a remarkable reduction. Look at the stress region. 5% became 31%. Look at the scarcity. 3% became 7%. So water is going to be a very scarce material. Therefore, it is very important that we must find cheaper ways of purifying water for the humanity. If you look at the water purification technologies, we have chemical technique, we have biological technique, we have mechanical technique. There are a variety of technologies. And of late, dear colleagues, membrane separation is gaining a lot of momentum worldwide because we can control the porosity, we can control the flexibility, we can control the hydrophilicity and hydrophobicity, and we can control the mechanical properties of the membranes. Membranes have a lot of advantages: high porosity, high polymer strength, and good elongation. Good flexibility. You can see some of the membranes are extremely flexible. Good chlorine tolerance. They have lots of fascinating properties. If you look at the totality of water purification process, we have microfiltration process, which can remove E. coli, macromolecules, colloids, bigger particles. Ultracentrifugation process, we can remove viruses and proteins. Nanofiltration process, it can remove small compounds. Reverse osmosis can remove ions. When you use membrane, there's always a problem called membrane fouling. This could be due to organic absorption, colloidal material, biogrowth, scaling. There are a lot of ways we can avoid membrane fouling. Dear friends, my group, what we do is we collect the cellulosic material from environment, from agriculture land. We collect the cellulose waste material. And then we do an acid treatment. And finally, what we get nanocellulose. My laboratory is capable of making nanocellulose from renewable resources, from agricultural waste. These are all agricultural waste. It could be coir, it could be pineapple leaf, it could be sawdust, and we are able to make beautiful nanocellulose. The first part of my talk, I'm going to talk to you how we utilize for removing dyes. Probably you all know that water is increasingly contaminated with the dyes, and dyes are being used for textile applications. So one of the important things we did is we looked at the commercial filters. Commercial filters that we use today are bilayer membranes. You know, this is a commercial filter, bilayer membrane. So what we did is we gave a coating with nanocellulose, which we prepared in our laboratory. This is a nanocellulose coating. Dear friends, once you do that, we also did some chemistry. This is nanocellulose. We react to the Melton's acid, and we introduce CO minus group on the surface of nanocellulose. We make the nanocellulose, electronegative. And I wanted to show you a beautiful separation process. My PhD student took the dirty water containing crystal violet dye. This is crystal violet. This is the commercial filter that you get in the market. You see, the efficiency is not good. This is the coated filter of the nanocellulose. my PhD students go to the cellulose surface. And this is chemically modified nanocellulose, this CO minus group. You can see that by chemical modification, the efficiency has gone up dramatically. Now we are discussing with companies to scale up this process. And my group will be able to supply very good filters to many companies in South India. And you see, this is a mechanistic approach. This is a coated filter. And when you filter the dirty water, all the crystal violet is stopped on the top surface of the filter. And what's the mechanism? Electrostatic interaction. So this is the modified cellulose. This is a crystal violet dye. And you see this electrostatic interaction. So all these dye particles could be stopped on the top surface of the filter. Now, let me show you another important issue. Probably you all know that one is increasingly contaminated heavy metals, like chromium, like lead. Look at the equilibrium absorption of chromium using nanocellulose filters. Equilibrium absorption could be something like 95 milligram per gram. Not only chromium, dear friends, we can remove nickel, we can remove cadmium, we can remove lead. There are 3 types of graphs here. The blue one is you simply use rice straw. Our great grandfathers used to use rice straw fiber to purify water. It's a good idea. You get 50%, 55% efficiency. If you go to micro length scale, you get 70% efficiency. Dear friends, please look at the red one. If you go to nano length scale, nanocellulose, you get 90, 95 to 100% efficiency. We can remove all sorts of metals. So we are going to make again filters for the villagers of India. Now, we also made use of nanocellulose filters to remove bacteria and viruses. Bacteria are bigger in size. So by filtering the water through our filter, all bacteria could be stopped on the top surface of the filter. You see, size exclusion principle. But dear friends, we want to remove viruses. They are very small. We were suffering from virus pandemic for 3-4 years. If you want to remove viruses, you have to do a treatment on the surface of nanocellulose. You introduce massive positive charge on the surface of nanocellulose. Then there could be electrostatic interaction, and you can remove viruses. These are the logarithmic reduction value of bacteria and viruses. This is for bacteria, this is for virus. We are able to make such pretty nice filters. Dear friends, we did a very nice work with Slovenia some time back. My student went to Maribor on a European fellowship. And what we did is we made hybrid construction of PVDF and nanochitin. We are also able to make nanochitin. When my colleague was using only PVDF for removing indigo carmine dye from water, the efficient separation was only 2.3%. But dear friends, when we hybridized PVDF and nanochitin has been made from crab shell. We hybridized it. Look at the efficient separation of the indigo carmine dye, 88.9%. So nanochitin is also a very, very fascinating material. So to conclude the first part of my lecture, dear friends, we are able to make nanocellulose renewable sources. And we are able to make beautiful filters for the common people to remove dyes, to remove heavy metals, to remove bacteria and viruses. And now we are also working on removing nanoplastics from water using nanocellulose filters. Now, the second part of my talk today is how nanotechnology could be utilized for health security applications. My group is very active in making nanoscale scaffold for tissue engineering applications. And in this talk, I'm going to talk about how we make this nanocellulose nanomaterial platform. We do electrospinning process. We do a lot of electrospinning process. We also do 3D printing process. We also do a lot of lyophilization process for tissue engineering applications. And there we utilize particularly nanocomposites. So the advantage of nanocomposite is you can control the size of the particles and you can make a variety of structures. You can modify the surface structure. You can control the porosity. You can improve the durability, surface bioactivity. So what we really do is we make use of a nanofiller and put into a solvent. We dissolve a biocompatible polymer. It could be PLA or PCl. Dissolve in a solvent. we make a slurry, and dear friends, we go for electrospinning process. So my group is very active in making electrospun biocompatible scaffold for tissue engineering. And we optimized a series of parameters: polymer concentration, a clay contents, applied voltage, moisture content. I'm going to show you some of our nice work. One of my PhD students made use of PCl, polycaprolactone. And then we introduced different content of polycaprolactone in dichloromethane solution. When you see 2-8% of PCl, 4-8% of PCl, 8-8% of PCl, and 10-8% of PCl. When you use 10-8% of PCl, you see you get beautiful fibers. Otherwise, you see lots of beads. So polymer concentration is very critical when you do electrospinning process. Similarly, we also looked at the nanofiller content. You see, we have made use of clay, biocompatible clay. You can see this is a different concentration of clay. The first one is 0% of clay, 1% of clay, 5 and 9% of clay. Dear friends, if you look at the last one, 9% of clay, we got very nice fibers because the clay increases viscosity and we got beautiful fibers. We also looked at the voltage. So electrospinning process, you can change the voltage because the solution has to be electrified. You can see this is, if you look at this is the 8 kilovolt voltage and this is 15 kilovolt. When you use 8 kilovolt voltage, you see you have lots of beads. It's not good fiber. And when you use 15 kilowatt, you have beautiful fiber structure. Now, I want to show you some interesting work from literature too. Look at the nice SEM photograph of neat PCl. This is a neat PCl, polycaprolactone. This is polycaprolactone with 1% of nanofibers. When you introduce 1% of nanofibers, you could get very strong fibers with a smaller diameter. People also have introduced different types of nanomaterials for electrospinning process. This is, the first one is polyurethane matrix with unexfoliated graphite. You see the graphite is completely unexfoliated. This is thermally expanded graphite. You can see a good level of exfoliation process. This is a solution process. Very good exfoliation process. This in situ polymerization process. Dear friends, if you look at solution process, in situ polymerization process, we can see the graphite, expanded graphite has been uniformly dispersed. Let me also show you another interesting observation. We introduced different types of clay particles into polystyrene. You can see that this is neat polystyrene. The second one is just 1%, 4%, 8%. If you look at 1%, the clay is uniformly dispersed. But if you go to 4 and 8%, you see a lot of aggregation process. So what I want to say is, whenever you put nanomaterials into polymers, you have to find out the threshold concentration. If you increase more than a certain level, there will be a lot of aggregation process. Another important parameter to be controlled for electrospinning is the moisture content. You can see this is electrospinning of polystyrene. The first one is the moisture content is less than 25%. The second one is moisture content something like 31 to 38%. This is 40 to 45%, 50 to 59%, 60 to 72%. So if you increase the moisture content, dear friends, you see lots of nanoscopic holes on the fiber surface. And you can see the SEM photograph of polystyrene, where the electrospinning chamber humidity was 50%. See, when you have a high content of humidity in the electrospinning chamber, you know what happens? These water vapor impinge on the surface of the electrospun fibers and then make an impression. They make fine holes. And these are also very, very important for tissue engineering applications. You can see the atomic force microscopy of nanoscale porous material, where we have changed the porosity. Now, I wanted to show you when you do electrospinning process, look at the electrospinning of PLLA with the hydroxyapatite. PLLA, the problem is hydrophobic. They're not very compatible with the body. So if you make a combination of PLLA and collagen, or PLLA, collagen, and hydroxyapatite, you can see the contact angle decreases. That means the system is more hydrophilic. So my group is able to control the hydrophilicity of the electrospun fibers by combining with variety of materials. Another important problem I wanted to tell you is when you make a scaffold by electrospinning, the mechanical strength of the electrospun fiber is very important. Look at the neat polycaprolactone. This is a very important polymer. The modulus is low, the strength is low. But dear friends, if you just put 0.5% of carbon nanotube, you see the modulus goes up, the strength goes up. So by introducing nanomaterials, the mechanical strength of the scaffold could be remarkably increased. I also want to show you another important issue. You know, after a couple of months or a couple of weeks, the scaffold have to disappear. But the tissue regeneration is complete, the scaffolds have to disintegrate. I want to show you a very important graph. If you look at the neat PCL, the weight loss as a function of weeks, they're not disintegrating. So it's bad. But if you put carbon nanotube into PCL, you see the disintegration becomes faster. This is a very important point. Introduction of nanoparticles strengthens the scaffold. Introduction of nanoparticles increases the biodegradation of scaffold. Dear friends, we do a lot of work with animals because these have to be tested. This is a work with the guinea pigs. We make sacrificial wound on the guinea pigs, and then we close the wound with electrospun system. Okay. I want to show you the totality of the process. This is our electrospinning process, the horizontal electrospinning process. And we are able to make such beautiful scaffold. If you look at the internal structure of scaffold, they are all electrospun system. And then you make a sacrificial wound. And the wound is closed by this tape. And this tape contains a little bit of nanoparticle. It could be zinc oxide. It could be titanium dioxide. So we carefully select nanoparticles. You see, dear friends, after a couple of weeks, what happens? The wound is completely healed. No scar on the wound. Why? Because you have very high level of angiogenesis taking place, cell migration, cell proliferation, angiogenesis taking place. And you can see this is our scaffold material. Now we are commercializing the scaffold by working with a couple of companies in India. And you can see this is our PCL with nanoparticles of TiO2. The TiO2 nanoparticle size is something like 50 to 60 nanometer. And we just are only 1%, 8% of TiO2. So tremendous healing effect. But dear friends, I also want to tell you that if you increase the concentration of nanoparticles, this is actually 6 to 8% nanoparticles, TiO2, in PCL. Introduction of higher amount of nanoparticles is very dangerous for the tissues. You have tissue damage, tissue death. Therefore, if you introduce the required amount of nanoparticles, you have excellent healing effect. And why the healing effect happens? Cell proliferation, cell migration, wound healing, and angiogenesis. And you can see this is a neat PCL. You can see histology. This is a neat PCL after 5th day, 10th day, and 20th day. This is PCL with 1 to 8% of zinc oxide. Remarkable difference in the histology. The same thing you can also see another set of samples we have done the histology. So very small amount of nanoparticles makes a remarkable change in the tissue regeneration. I also want to tell you another important thing. The scaffolds have to disappear after a couple of weeks. You see, this is the 5th day. This is neat PCL. This is PCL with 1 to 8% of zinc oxide. You can see disintegration of the PCL is much faster when you have 1% of zinc oxide. I also wanted to show you the quantified wound healing process, the scaffold we have developed. You see, this is wound healing, quantified wound healing process. This is a number of days. Dear colleagues, if you use only PCL, The wound healing is not very efficient. This is PCL. The wound healing is not very efficient. You see, the wound is closed, but you always have a scar. Look at the second one, PCL with the 1% of zinc oxide. You see, at the end of the 30 day, the wound is completely closed and you can see hair growth. You see, that's the beauty of adding a little bit of nanoparticles. Just 1% of nanoparticles of 60 nanometer size. Dear friends, we also made silver nanoparticles. We did the green synthesis of silver nanoparticles. And we combined with PBA. We went for electrospinning. And we made fantastic scaffold. PBA, silver nanoparticle scaffold. Extremely active antibacterial property, excellent biocompatibility, excellent wound healing. So this is another set of samples we have made with nanosilver, in situ synthesized nanosilver. We have also made yttrium oxide nanocomposite. This is neat PCL, 0.5% of yttrium oxide, 1% of yttrium oxide, 2.8% of yttrium oxide, 3.8% of yttrium oxide. Dear friends, if you just put, this is neat, this is the neat PCL. If you put just 1% of yttrium oxide, look at the mechanics. Very high modulus and very high mechanical strength. But if you add more, 1, 2, or 3, the mechanical properties go down. So we have shown that the right amount of nanoparticles make a remarkable difference. We also made titanium dioxide nanorods and introduced into PCL polymer. Look at again the mechanics. This is a neat PCL. This is just, the blue one is just 1% of nanorods of zinc oxide. And if you put 1% of nanorods of zinc oxide, a remarkable healing effect. We also made lyophilization process. I can show you, we made completely green scaffold for tissue engineering. Look at, we started with the gelatin, a natural polymer. We made use of hyaluronic acid. We combined them and we added a fugacite filler into it. And then we went for lyophilization process. So we made a beautiful scaffold material. This is one of my brilliant PhD students. She's right now in Australia. And she made very nice porous scaffold material, combining green material and green filler. And look at the porosity of the material. This is without any green filler. This is 2.8% of filler. We have optimum porosity. And we looked at the porosity by tomography, 90.6% of porosity. That means the tissue regeneration is extremely fast. Dear friends, we also introduced gelatin with acrylate hybrid patch. You can see this is the mouse model we have used. We have made use of gelatin with acrylate material. We introduced a growth factor. This is our control. And you can see we made a sacrificial wound, and the wound is closed by gelatin with acrylate growth factor also introduced. And then we introduced a polyhydroxy butyrate material. And we have irradiated for cross-linking the material. Dear friends, look at this slide. The swelling of the material with the body fluid. You can see this is a highly biocompatible material. And we have found that the cell proliferation, cell migration, angiogenesis is super in this material. This material is also we are going to scale up as a wound healing, wound dressing material. And finally, dear friends, we also made use of 3D printing technology. For example, I have just a couple of slides. This is 3D printed PCL. We modified the PCL with the plasma to introduce positive charge. Then we have made gold nanoparticles. Gold nanoparticles have been made electronegative by a surface coating. We introduced these gold nanoparticles onto this plasma-modified PCL. Gold nanoparticles have been immobilized because of electrostatic interaction. And dear friends, this is an excellent scaffold material for wound healing application by 3D printing. This technology also we are going to scale up. We also made very nice work for making heart valve with my colleagues in Brazil. Look at this is polyurethane, medical grade polyurethane. The mechanical strength of the medical grade polyurethane is only 17.5 and modulus is 37.5. Dear friends, if you add 5% of nanocellulose made from plant, you see the modulus become 992.4, a tremendous increase in modulus. Effectively, my colleague in Brazil and I, we made nanocellulose polyurethane prosthetic heart valve using medical grade polyurethane and nanocellulose. We also made quite nice material for artificial skin. You know how we made by introducing nanoparticles into natural rubber latex. You can see this sort of very flexible conductive material has been made by introducing nano CNT into natural rubber. You can see the conductivity increases, the volume resistivity decreases. So we made very flexible conductive rubber for artificial skin. In summary, dear colleagues, we have made fantastic scaffold by electrospinning process. And we are able to scale up this technology with the park I am heading into under. We made fantastic scaffold material for 3D printing. We made beautiful porous scaffold by lyophilization technique. And this is a great contribution for healthcare industries. So we are scaling up all these technologies with a science park in Trivandrum. Thank you very much for your patient hearing. This is some nice pictures of Kerala. Thank you.
Thank you so much, dear friend. This was so beautiful. This was just a glimpse for our friends who are listening. This was just a glimpse into the results of our friend Sabu Thomas. He could go on like this for hours and we would still be amazed. So this was really beautiful. And also this, there are so many examples which can help, particularly after the wars, that healing is difficult, but with these technologies that Sabu now showed, healing could be made much faster, and I believe we can now move to the second speech, and then we'll go question and answer after the next half an hour. So the second presentation is by our good friend Eduard Alarcón. He comes from UPC Barcelona in Spain, and he is actually from computer science, the head of quantum computing group, and we're going to hear a different perspective, which I believe is really important, because we know recently that this quantum computing hardware is getting so strong, but we have no useful algorithms that could use this strength. And once one could get like more useful algorithms than the ones that we are used to, like Grover and Shor and Deutsche Joscha, we could really make like a massive progress into the future, like solving lots of difficult challenges. So that's why I'm really looking forward to your presentation. Eduard, please, the floor is yours.
Again, very good afternoon, everyone, and good evening or good morning, depending upon the time zone you are now. It is a true pleasure and generally a privilege to take part in this seminar devoted to this very compelling and timely topic of science and technology for human security. I would like to also to thank Gary Jacobs, with whom I've been interacting in the past months, for introducing me to this very selected group of individuals. For me, is a true honor. So the very field of human security as an overarching theme that encompasses a variety of grand challenges of humanity and stresses the interplay and the interaction among and across them. It was a new concept for me until a few months ago, but I immediately intellectually caught my attention. So it's a very relevant matter, not to say that perhaps it's the most relevant matter. So in these times of turbulence and crisis, it's time for action. In this particular context, I will try to be perhaps a bit both evocative and provocative in revisiting a couple of technologies, quite different in the terms of how mature they are and how they can be used towards pursuing human security. So I will try to avoid both utopian and dystopian positions. I will just try to describe facts and ideas and concepts and proposals. It's true that AI it's a very misleading field in the sense that There's far more than just language models for AI. I would like to share with this very selected audience, given that this is a very multidisciplinary audience, 3 selected uses of AI that, to my humble understanding, could bridge towards human security. Now, for quantum computing I wouldn't say it's a brand new field, but it's quite an emergent field. So I will try to highlight how to incorporate the ethical implication, the social impact, and human security upfront, the sooner the better, into not the very use of the quantum computers, but the design of this platform. But that would require a bit of an introduction, given that, again, the audience is quite multidisciplinary. So with that, let me start first with a philosophical preamble. I'm sure that all of you know that in science generally, in parallel to the scientific method of experimentation, there's a scientific principle that it comes a bit from the very field of dissipative systems and complex systems and entropy, and again, but it says that in times of uncertainty, it's very important to manage complexity, to make complexity less complicated, more intelligible, and that has to do with the way we understand the interactions and the interplay across the very scientific fields and how they interact with human security. Let me reinforce what I think is the obvious. Technology that comes from science is neither good nor bad, is not even neutral. Technology is ambivalent, and it depends upon the type of value we provide in the technology, not in the usage, but in the very design process of the technology. In that sense, adding purpose could be just because there is a pro bono application in that technology, just because we consider the ethical implications or the grand challenges of humanity or human security as that integrated framework. So I would like to postulate a bit in this very short presentation, which is not even a talk. I'm just eager to have a conversation with you all, perhaps a Socratic discussion. It's for all of us to understand this field. I would probably try to postulate that the very field of complex systems might come at rescue in understanding the interplay of these SDGs and related this theme of overarching human security. Now, for the AI as a technology, I will first start by talking about AI to guide better inter-multidisciplinary action. Then I will try to identify trends in AI. I will talk about graph neural networks or geometric learning. And then I will talk about physics-informed machine learning. These are 2 very emergent fields that I think that they have a very strong impact on human security. And then I will very shortly mention an ongoing project on AI for identifying and educating human talent. Then I will talk about quantum computing. Probably all of you know that the UN declared this year the International Year of Computing. I think it's very timely to incorporate these aspects of human security, but it's a bit of an unexplored field, so let me try to make a position on that field. I could talk for hours. I only have 30 minutes, so fasten your seatbelts. I'm going to fly over the slides. What I want is just to share some insights and then go to a conversation. Let me start with internal multidisciplinarity. Probably this is not new for none of you. Since a few years ago, there already exists scientific evidence about the notion that interdisciplinary research results in more impact, scientific impact, but also social impact. It just takes more time. And now this is based on data. Now, and accordingly, a variety of agencies and institutions, including academies in a variety of regions in the world, they are betting on inter-multidisciplinarity from a variety of standpoints. Let me just briefly recall, because inter-multidisciplinary, they are 2 terms that they are quite different. They share that they are difficult to pronounce, but they have a very crisp and clear definition, which is different. This comes in conversation with a colleague in the Academy of Science and Engineering in Brussels, in Belgium. So if you have in mind sort of a Venn diagram description of the different disciplines that compose a given scientific field or science at large, interdisciplinarity is that area that is at the overlap between adjacent disciplinaries. Now, whereas multidisciplinarity is the combination, the articulation of different disciplines to achieve a goal or to articulate a team or the like. That interplay or that combination can be in content, in concepts, in insights, or in methods. Well, is there a way to combine inter and multidisciplinarity? Now, in some contexts, there has been a proposal to model a given system. Let's see, a university. Universities in a given region, in a country, continent-wide, worldwide, as a system like this. It's a bit of a simplification, but it could be a matrix where in one dimension we have the set of disciplines or scientific knowledges and related technologies, particularly trying to foster their interplay and overlap. And then in the vertical dimension would be how to combine these disciplines and these interdisciplines to align to address humanity grand challenges, SDGs. Now, in practice, reality is not as simple as a matrix, but the concept is there. And reality is not just a Venn diagram. What you have within each of the scientific disciplines is probably like a network of knowledge, like a graph that describes this knowledge. So let me go into, is there a possible way where AI and data can assist in creating these knowledge maps, out of which we can foster better interdisciplinarity and better multidisciplinary action for, in particular, aiming human security. So there exists methodology where you can distill knowledge from just research papers, identify the correlation, the co-occurrence of the concepts and the terms, and then just classify this into the dimensional space and then clusterize this and derive a knowledge graph in the form of a correlation matrix. So let me just instantiate and provide an example in the way you could apply that type of navigatable graph-like representation of the knowledge map of a given institution or a country or a field in the form like this to try to address better the pursuit of one SDGs or a variety or a collection of SDGs, all of them concurrently as human security tries to pose. So you could identify the areas that are combined and articulate multidisciplinary clusters. Let's say this could be a task force or a collection of individuals or a consulting team or assisting a government in their decisions and try to assess a particular example. This is coming from true science from one moderate sized university, my university, and applying to one particular example of an SDG. Now, you see that, well, I'm gonna not go into the nitty-gritty details, but this is representations like this, where you can identify and perhaps even consider the holy grail of scientific advisory, which is trying to predict emergent areas where the future should go, like, which are the scientific areas where there is potentially more fertility in the interaction, which is the overlap of emergent fields. So this is requiring a collection of AI tools, language identification and filtering, natural language processing, embeddings, clustering, and eventually the graph constructions. You will see that in the presentation today, graphs in the sense of this mathematical instances or bodies will abound. So I humbly think that a representation like this could also tackle crucial aspects of education. I'm an educator myself. I resonate very much with the mission of the World Academy of Art Sciences. Today, we're not talking about education, but I'm just recalling aspects by Janani and Gary that say that, well, usually hitherto, scientific disciplines in an educational context are disjoint. So a representation of scientific knowledge like this, by virtue of using appropriate AI techniques, could foster more inter and multidisciplinary education. Okay. Even it would be a way to, by identifying the way the scientific knowledge is structured and organized, orchestrate or articulate task forces to pursue the SDGs. This is something we've been trying in other contexts for some time now, but it's not for me. I realize that there's an overarching conceptual umbrella that encompasses all the SDGs, which is human security, and that's why I think this is relevant today. That would be an example of using AI. So the way the World Academy is defining human security as the interplay between these SDGs has been providing some traction. We start to identify scholarly papers that talk about the interlink and the interplay between among and across SDGs. I'm just mentioning a few. I would like to highlight this work from Felix Laumann and the University College London. I think they are using graph theory and AI to identify in a quantitative manner, yet ironically, graphs in the form of nodes and edges and weights are mathematical constructs that are very easy to understand. They facilitate the intelligibility of that interaction. And then following again, which are new trends in AI that might be relevant for human security, I would like to identify to the audience that there exist graph neural networks in which, in a sense, there is a machine learning architecture that is also called geometric learning. It's a moderately recent field where, apart from classifying very large dimensional spaces, you can identify, learn, model, and predict the geometry, the network, and the graph that is within a complex system. I think that these are very powerful tools and very powerful ideas in pursuit of human security. Now, following this first section devoted to AI, where I wanted to identify new trends in AI, but let me close in talking how these graph neural networks and AI to derive graphs could also be used for something that it's more than just educating, will be in identifying, educating, fostering, and mapping talent. There's an ongoing project, both by Gary Jacobs and myself and other colleagues in a local foundation for talent, where we're trying to come up with a taxonomy of what talent is and mapping it or having a cartography through AI. That would consist in identifying talent, trying to measure talents without falling into the trap of the tyranny of just getting into metrics of talent. Talent is very difficult to measure, but can we describe the attributes that compose talent? And if so, can we educate it or identify? And for individuals, but also for groups, including diversity and complementarity across talents, and then ending up with maps of talents, group-wide, region-wide, city-wide, institution-wide, country-wide, worldwide. And that would also facilitate mapping inter- and multidisciplinarity, not for the abstract scientific knowledge, but for individuals and for collectives and for the community. And we are even trying to, if ever possible, trying to capture a measure of the very elusive genius talent, because we postulate that very few exceptional talents, either already explicit or hidden, a few of them that not unexpectedly they need to encompass and include human values, humanism, which defines the mission of the World Academy. If ever we are able to identify this very exceptional talent, a few of these individuals could make a change in a given transition of the world. So I'm just closing this first part of the lecture by, well, it's not even a lecture, it's just an informal conversation, but just by introducing another field, which I humbly think might be very relevant to perceive human security. It's the very field of physics-informed machine learning. So I know that this originally was devoted to nanotechnology. Let me talk a bit about physics without going into a lot of details. So probably most of you have heard about this physics-informed neural networks, where instead of everything coming from data and ignoring the a priori understanding of the world we have in the form of the laws of physics, you can incorporate some laws of physics and then requiring far less data, orders of magnitude less data. So this is both philosophical, practical, is an engineering approach, and it has implication. One very simple yet very powerful example would be machine learning methods which excel in classifying problems and etc. and interpolating functions and in mimicking agents. It's not very clear that they excel, but they try. They usually very much fail in modeling dynamic systems and dynamic complex systems. And this is because the fact that they ignore the dynamics, the differential equations. So one example of physics-informed machine learning will be to incorporate the differential equations up front and allow the neural networks just to do a regression and approximate the nonlinearity so that we can better understand and model these systems. I'm just mentioning because this is an example of applying a PINN to climate. I have the impression that most SDGs, if not all of them, they are spatiotemporal processes that come from complex systems. And therefore, physics and machine learning has the potential to be able to understand and model more SDGs, human security, and all these bridges. And this potentially might be true for another very difficult angle of the problem, which is capturing different time scales. This is an example of applying this problem for different time scales in again, climate prediction. So another problem of SDGs, beyond being spatiotemporal process, they have multiple time scales, short-term, mid-term, long-term. It's very difficult to capture that with models. And I have the impression that physics information learning might be a way. Okay. That was all for my half side of this discussion. Let me now change gears and go to a quite different field, which is the very field of quantum computing. That's much more related to nanotechnology. I'm assuming that most of you are familiar, if not experts in quantum computing. So let me try to quickly revisit this very field, which has been migrating in the past years from physics to engineering, and now it's encompassing a variety of disciplines. It's a very multidisciplinary field by definition and by inception. New generations now are being trained in this very field. And I wanted to try to think and speculate about the implications for human security. So remember that we're not talking about a general purpose computer. It's just some computation based upon the laws of physics, three in particular, superposition, entanglement, which come from, in a sense, emulating a synthetic atom. And that type of statistical compute, in principle, has the potential for a very few selected set of algorithms. Aleksander was mentioning Shor factorization. We can talk about others. It could be sorting, mainly optimization. Quantum computers have the potential of having an exponential speed up. And it's not just speed that matters. We're talking about potentially sometime from now being able to model, simulate, and solve problems that are literally intractable by the strongest and most powerful high-performance computers in the world. So that's the level of disruption that quantum computer promises. Where is it now, quantum computing? Where there's a tangible reality. Now we're talking about quantum computing chips operating at cryogenic temperatures encapsulated into a full stack architecture that can run algorithms up to thousands of qubits. I will identify the challenges and the Achilles heel. Mainly scalability is one. And the other one is mainly error correction. They are still very prone to errors, very, very fragile. But I will try to share the roadmap, and at the end up with, again, a bit of a philosophical discussion on how quantum computing optimization in particular could be related to human security. This following 3 or 4 slides are very, very, very essential and simple. They have been used for outreach. So forgive me if some of you is a true expert in quantum computing, but I think that they are interesting as a metaphor to understand the underlying principles of quantum computing. So in a sense, a qubit, which is the unitary element of a quantum computer, it's sort of a controllable atom. You can make changes of some quantum attributes, like the spin of that synthetic atom, etc. So you could visualize that we have a collection of elements of qubits that we can control and manipulate, and it's through the way they encode the information and the way they interfere and entangle that really we can achieve exponential speed ups. For those of you with a stronger scientific background, well, one qubit alone, it's in essence a multidimensional complex Hilbert space that talks about the capability to incorporate information. But the interaction across many is also very important. That interaction could be in the form of interference, of quantum interference. Remember, you're talking about principles that only happen at that atomic and subatomic scale, and how to leverage that interaction at a distance for quantum computing. I'm not just talking about quantum internet. That's also a possibility, and I'm eager to discuss if you want during the discussion, but let's talk about distributing entanglement across qubits in a quantum computer. And the third will be covering these two elements, the way quantum computing is some type of probabilistic computing. So why is this potentially magnificently better than the other type of computer? It's not just about parallel computing. We are allowing nature to compute, the laws of nature, in particular the laws of quantum physics. So you could visualize that we have all these qubits, all these spinning tops in a billiards table. They interact, they codify information unless they relax and they minimize the multidimensional function. That's what nature does. Can we use it to compute these elements? And it's all about natural optimization by the laws of physics. Achieving this is an extreme engineering challenge. I think that I can skip these two slides. I guess all of you are familiar with what qubits are in terms of their power, but you see the potential is the richness of this information encoding and to the power of n potential of computing by virtue of the superimposed states and entanglement. Qubits are very weak as well. They tend to decohere, so it's very important to compute and process that quantum information before elements decohere, and it's very difficult to measure by principle. So these are the uniqueness of quantum computing. Despite this situation, the status quo of the very field of quantum computing is the following. I would say that we are a bit reproducing the ENIAC moment. This is the ENIAC, for those of you who remember, and the ARPANET, the deployment of the first internet. We are now just developing large machines where a small reduced number of qubits, but they are fully fledged, functional, and they can run algorithms. So in principle, you have just the very quantum chip itself at the bottom, close to the absolute zero, the lowest temperature, not on Earth, but on the universe, if you wish. And then you are able to control and read out this quantum state and the manipulation of all of them and the interference of all of them to run algorithms that run probably in classical electronics that are in the rooftop of this structure. Still, these are beautiful engineering elements. So how does the future look like in the technological roadmap? And I'm using one from a company, but scientists in academia also more or less bet on the same idea. Probably will need to combine multiple of these chiplets. There's a limited amount of qubits you can accommodate in one element only. So we're talking about leveraging communications to interconnect modules. And sometime from now, we start to envision data centers which are quantum computer centric. So the idea is consider quantum communication networks, sharing entanglement as a scarce resource to be able to share quantum states and qubits and apply remote gates so that we are able to reach the million qubit element where it's a break-even border where we understand that really quantum computing will make a difference. It's just that understanding, designing, and using quantum computers itself, it takes some time. So there's a slope of learning. So the community now is talking about migrating from quantum awareness to quantum readiness, so that there's a task force once this technology can be applied for relevant problems. There is a lot of change now from physics to hardware to software. There's a lot of full architecture design and co-design from the software to the operation of the quantum chip. We are using instructions that look a bit like just programming directly on the machine code. There is a very important problem of mapping this algorithm and the related interaction graph to a very connectivity constrained underlying quantum chip. That process is called compilation and mapping. There's a very active field of research. But the summary is that these machines already exist. You don't need to know about quantum physics. You don't need to know even about the electronic implementation of it. You can run it on a cloud server and mainly use commercial software packages to run main optimization. So optimization both in quantum annealers, which are in a sense the analog wave version of this quantum computing, and the quantum approximate optimization that it's based on the gate formalism, particularly the quantum unconstrained binary optimization or Kubo formalism. Every problem that can be mathematically posed as an optimization could potentially be solved in a nutshell by a quantum computer in each side. So to finalize this and go towards human security, let me try to open the discussion on well, all these quantum computers, well, potentially what for? In principle, again, they have very limited but outstanding functionalities, either for simulation, emulation, search, ranking, ordering, factor optimization or optimization as something which is a bit the backbone of many algorithms, including AI, but not only. And that is what really results in a potential impact into a variety of domains, all of them related to not only to companies and scientific domains, but human challenges. This is what some engineering journals identify as potential examples of quantum computing, drug metabolism, material science in particular, to synthesize and discover alternative pathodes in energy management in batteries, CO2 sequestration, because that's again a problem of material science, fusion reaction. It's very difficult to solve these equations, which are fundamentally quantum, and they could potentially be solved by a quantum computer. And then, particularly in biology and chemistry and everything that comes from it, quantum computing and quantum optimization are a natural fit. Now, for those of you who have been tracking the field, there is a lot of excitement. I have to admit that the quantum computing is a field with a lot of excitement, and I don't want to say hype, but it is. It's an exponential hype. I'm trying to tone down to just identify the factual reality of what the machines are and what the science can deliver. There is a very recent combination of quantum computing and machine learning. This is not accelerating machine learning. This is leveraging the very intrinsic and inherent capabilities of quantum computers to do machine learning. For those of you who have a background in machine learning, this is akin to kernel methods. We can implement kernel methods to do machine learning by the natural way of a quantum computer to do that type of classification. And I think that, well, it was a bit mysterious, but I think that I'm more or less following the time. Let me just finalize with one slide to foster the discussion. And it's, if I started with a philosophical preamble, this would be a philosophical epilogue. So I think that in just 10 minutes, I tried my best to convey that quantum computing could be a revolution on how we can apply optimization at scales that are unheard of by humanity. But then the intellectual question, the human question arises, what to optimize? Then we are talking about the tyranny of this figure of merit or the cost function. So we have seen what has happened with AI, with the figure of merit was because of business models, maximizing network exchange, maximizing human engagement. And we have seen what that has resulted in society, more individuality, attentions being trapped, etc. So I don't want to go into that domain. That I think that we all of us, we have an impression. So that's what I think that quantum computer will be a double-edged sword, will be an ambivalent technology. I'm not claiming it will be for good. It depends upon its use. I'm just reflecting that it can be used for optimization at dramatically larger scales. And therefore, it is crucial, I humbly think, that we go from just humans in the loop to human values in the loop. This is perhaps subtle, but I think this is very important. If we just have human behavior in a loop that optimizes, we can do anything with that. It's a matter of incorporating human values in the loop. And with that, you could potentially consider this. If I might use an analogy, this is very similar to something where the World Academy and some of you have been thinking and writing about. If humanity or economics of humanity is driven just by gross domestic product, that aggregated metric that describes economic growth not only describes it, but drives it and biases growth. So there are counter proposals of what to optimize. I think that analogously, the same applies here. I also think that's very important in a society that's becoming very individualistic, and that some might think that human security is now worsening potentially also because of that. It will be very important that we don't incorporate individuals alone in these optimization loops, but relationships, choral, community at any scale. That's another final thought. And of course, I truly think that human freedom, but mainly value-centric human judgment, that would be out of any loop of control or assistance and of course of optimization. So as a summary of this very short discussion, I would like to finalize by saying that AI has the potential to affect human security, particularly in modeling complex networks and systems. And quantum computing could, by aiming optimization, also do so by encompassing human and humanist values to address human security. And this is something that resonates a bit with the notion that we've been discussing together with Gary Jacobs, mainly symbiotic AI systems, but that would be probably the topic for the discussion. And with that, I would like to stop my presentation. Thank you ever so much for your attention.
Many thanks, dear Professor Alarcón, dear Eduard. This was really a beautiful talk, and I believe now you actually combined two very important topics, the talent search and the quantum computing, and this talent search, I believe, is really important if we want to get future algorithms for quantum computing. And also, I noticed we also have the other Vice President, Nebojša Nešković. We have ambassadors Ludwig Toplak and Francis O'Donnell. We also have some very good guests. So, dear friends, many thanks for joining us. But we also have some questions. I think the first question was in chat for Professor Sabu Thomas by Amadou. Professor Thomas, did you manage to read the question? Could you perhaps respond to this?
Yes, I managed to read this interesting question by Amadou. One of his questions is, nanoparticles have fantastic properties. He asked about the toxicity. That's a very important question he asked. Of course, many nanoparticles are toxic. What we do is we do a variety of chemical treatment on the surface. For example, pegylation process. Polyethylene glycol, we treat the surface. Sometimes we treat the surface with chitosan, a biocompatible polymer. Sometimes we treat the surface with PLA or PLGA. So surface treatment is a way to alleviate toxicity. And if you use extremely small particles, the surface to volume ratio is so high, they tend to be more toxic. Therefore, we always take something like 50 to 60 nanometer size. If you increase the concentration of nanoparticles in the scaffold, it tend to be more toxic. So optimum amount of nanoparticles, the right size and surface coating, we can avoid the toxicity. He asked another question. He asked me how to control the porosity of electrosponge system. The porosity can be controlled by controlling the electrospinning parameters. The voltage, the concentration, nature of solvents. We can also control the humidity in the electrospinning chamber. When the humidity increases, what happens when you have evaporation from the surface of the electrospun fiber, the water vapor impinge on the surface. So dear Mr. Amadou, by controlling the electrospinning parameters, we can control the porosity. Additionally, my research group also modified the electrospun fiber with sodium chloride. We also introduce sodium chloride into the system, electrospun fiber. And when you press it, and then we dissolve out the sodium chloride in water, then you can make macroporosity. Macroporosity is very important for tissue regeneration. And nanoporosity is very important for giving food to the tissues. So my research group is able to control the porosity. And this gentleman asked one more important question. Can we reuse the filter that we utilize for water purification? My answer is yes. We select a suitable solvent and we allow all the impurities to dissolve into the solvent. And then we recycle it and catch all these impurities. So we can reuse it, this membrane, several times. For example, our membrane for removing industrial dyes, we could use something like 20 times. So that's a very important question. This is called membrane fouling. After a few uses, the membrane gets sort of clogged. So we can clean them and all the dyes could be purified and we could recover. Thank you, gentlemen, for your excellent questions. Thank you.
Thank you, Professor Sabu, for these wonderful answers. I believe now we have a question for Professor Eduard from Donato. Donato is asking, how do we measure talent? How do we identify talent? It's probably not easy.
So that's a very, very interesting and very difficult question. I'm very sorry, Donato Kininger, that we cannot have a conversation. I don't have a closed answer to this. Of course, I admit that talent is something extremely elusive to measure. I would say it's as elusive to measure as happiness or love, but it is there, but talent is there. So we don't measure talent, but proxies to talent. It's an indirect measure. I think that what's important is that we concurrently measure a few things. Mental attributes, outcomes of your talent, encompassing soft skills that you're indicating. So there is ongoing, I'm not very much in favor of just reducing things to metrics, but I think that having talent as a collection of metrics, if I admit that we need to simplify this to metrics, having a collection of them, a vector of metrics, that might be a better way to trying to, if not measure, identify and bound where to look for talent and how to educate it. So yeah, I admit it's a very, very difficult part of the analysis. Anyhow, in that context, I think that AI properly used could be advantages in this notion that we can model talent as a collection of these metrics, and then the relationship between them as a graph, and then take it from there in finding things that are not very common, which is diversity of talents, group-wide talent, and then interdisciplinary talent, and the like. And of course, the final dream is to include or educate or identify human and humanist values there. I don't dare to put a number or a metric to that, but we are trying. So that will be my reaction. I'd love to have an open conversation, but I think this is very asymmetric and it's not possible. Aleksander, should I proceed with other questions?
Yes, I think you should go with the question of Professor Uros Kvelbar.
Yes.
Yeah.
Then there's another question from Uros Kvelbar. It's a very legitimate one, a very difficult one. The scientific community is very unclear. If I embed all the excess of hype in this field, quantum computing, would it really revolutionize machine learning? It's not very clear. Again, quantum computing is not about accelerating machine learning. When I talk to AI scientists and machine learning people that develop algorithms or implement chips, they want to see an advancement in speed, a twofold increase in speed, a tenfold increase. No, it's not that way. It's just that we have the potential to run some algorithms at a scale that are not solvable at all. But these algorithms are very particular, like optimization and etc. It's not a full-fledged computer. It's not a full-fledged neural network. And therefore, it's difficult to mimic a cognitive agent as we are doing in AI. Still, optimization is at the backbone of many machine learning algorithms. So that could be the possibility. And then we have this very recent field where we're trying to get hybrid systems, taking the best from both worlds. And then I have, if I may, a final question from Francis Martin. I don't see the name, apologies. How would you compare AI such as Grok to quantum computer? My blunt reaction is I never use AI myself. I'm a scientist. I don't use AI assistants. I haven't installed ChatGPT. I apologize. I know what Grok is an assistant. It's emulating a cognitive agent. So that has nothing to do with quantum computer, which is because quantum computing in principle only solves scientific functions. And then optimization, which is something very universal. And today I tried to make the bridge between optimization and the challenges of humanity, but that will be my position. And then I have a final comment from, I don't even know, it's GA. I hope it's not Gary Jacobs, it might be. I'm sorry, my computer is disconnecting, but somebody is saying, many thanks for Dennis. Gary is just, I think it's blessing the comments. No question, Gary. Thank you ever so much. I would be privileged to continue the conversation. I'm at your disposal.
Many thanks for these nice answers. I mean, there's still a lot of questions. Perhaps we go with a question for Professor Sabu. You mentioned that these wounds can heal better with your technology, and also that you can kind of help in cleaning up with a lot of this pollution. Could this be also useful in this after-war cleanup? You know, when there is war, there is lots of explosions and chemical agents and stuff like that. So how could nanotechnology help with that is our question.
Nanotechnology we could utilize to remove many of the pollutants in water, in soil. And we, depending on the nature of pollutants, we can modify the membrane surface. We can have electrostatic interaction, we can have pi-pi interactions. So several interactions could be introduced on the surface of membranes. So we are capable of making such beautiful membranes for a variety of applications. And Aleksander, some of the membranes, we are actually scaling up with some companies now. And my idea is to release a membrane to the local people so that they can clean their own water.
May I chime in for a second? I don't want to break the protocol, but then Sabu and Aleksander, this would be a true conversation. So today I was not talking about my own research, but back in the day I've been working in, for instance, in graphene-based nano antennas. I think that there is a lot of potential, apart from the fascinating research that Sabu was sharing with us today, in sensing pollutants and sensing viruses and sensing bacteria at a distance. So you can illuminate probably with wireless terahertz radiation a given region and identify methane, pollutants, viruses. This is an area of active research, particularly graphene, because of its properties. It exhibits a boost of conductivity in the terahertz band, and it allows you to implement very small antennas, nanoscale antennas that they could be pervasive in the body or in the structure. It's just that this is not advanced in TRL, and through deployment, it's still at the experimental stage. But I think that sensing is also a possibility, and it's a bit far-fetched. But we are also starting to talk about quantum sensing. Today, I just talked about quantum computing, but quantum technologies also encompass quantum communications and quantum sensing. We can discriminate molecules and compounds with an unprecedented level of accuracy through quantum-based sensors. So that's another area that could be used for pollutants and for harming molecules, I would say.
You can make use of photophysical properties of quantum dots for sensing.
Exactly, very beautiful. I mean, so many amazing opportunities. It's really, I mean, we are living in unprecedented times. There are so many amazing opportunities. We just need more people to join this research and like explore these opportunities so that we come to a better place. And I don't know, I mean, regarding these talents, I mean, Edward, you mentioned this quest for talents, and then also the difficulties in quantum computing when you have like very few useful algorithms. So what would you advise to a young person who is identified as a talent? What should this young person learn in order to do something useful in quantum computing in the future?
Well, the first advice, who am I to advise, Aleksander, but the first advice would be to try to experience the Leonardo da Vinci syndrome, which means to become not even a multidisciplinary student, but a polymath. Try to learn from many disciplines, because truly in quantum computing, to name a few, you have quantum physics, you have nanotechnology at the bottom of the quantum chip, you have electronics, you have computer architecture, you have algorithmics. Really, it requires a concurrence of all this scientific and technological disciplines. So that's why it's a bit challenging to create educational programs in quantum computing. I've been involved in some initiatives in Europe and in the US, and I'm also participating in some outreach programs to reach other regions of the world, all of the world. What I haven't seen, I have to admit, and that's something perhaps it was not clear enough in my presentation, in AI, nowadays, no one will be surprised if we talk about human-centric AI, ethics incorporated, but it usually came as a patch a posteriori. I think we do have the opportunity to incorporate ethics, the societal implications, and the purpose of address the SDGs upfront in the design phase. It's just that the students apart from the scientific disciplines, they should incorporate these humanist values in when educating these talents. So it will be more likely that some of this new generation of quantum computer engineers would pursue the challenges of humanity. That's my understanding.
Mm-hmm. Wonderful. Sabu, would you add something?
Yeah, sure. You see, AI is getting a lot of momentum. We also utilize AI for a variety of applications. We have a separate course on AI for polymer science. When you use AI for polymer science, if you look at the compounding process, we have multiplicity of additives. So using AI, we will be able to predict some of the properties. What could be the additive incorporated to the polymer? So AI is actually, I'm doing a lot of help in polymer science and nanotechnology. We have a special, a course for AI for polymer science for the students.
This is very interesting, Sabu. If I might chime in again, there is this very nascent field of AI for scientific discovery, where we're using AI to discover new science. When I was showing this scientific knowledge maps, this description of a given discipline, really new knowledge is at the border, at the frontier of this. That's what we do as a scientist. Can we use AI to discover molecules and compounds faster and better? Science can do that. The question is who owns that new discovery? Is it protected by just a company? Is it owned by humanity? Which is the purpose of that discovery. But it's true that we will witness an area of accelerated discovery of scientific structures, nanostructures, biological compounds, pharmaceutical compounds, accelerated by AI. I think that technologically that's very clear, very feasible. The question is, who owns that and what do we do with these new discoveries?
Absolutely, absolutely. Really, so many amazing possibilities. I mean, the future is going to be really so great. I see we have from Maharaj, well done, and from Jeffrey, we have philosophical perspective. I think this would be a question for Edward, if you want to comment.
I cannot see it. Which one?
It says, are you suggesting a philosopher's stone when we have water everywhere and not a drop of water to spare? So it's a bit more philosophical issue, but...
is it for Sabu or for me?
I think it's for Edward.
I cannot find... I cannot find...
Doesn't matter.
Can you say it again, Aleksander?
Philosophers have water everywhere and more philosophical approach to the issue. Anyway, I believe what we have covered now, massive breakthrough, massive progress, and also, I mean, our main goal is to attract. We cannot do it alone. So, one main conclusion would be, let's attract as many young, bright people to help in this endeavor and to really do the breakthroughs that we have been talking about, so that both nanotechnology and quantum computing and AI are going to work for the benefit of humanity. I believe we are allowed to be allowed until 6 o'clock, but I would like to ask our president, Gary Jacobs, for the final remarks.
Well, my remarks will be very brief. To thank you, Sabu and Eduard, and you, Aleksander, for a really stimulating, thought-provoking session in which you have taken the latest, most advanced breakthroughs in fundamental scientific research and shown their practical potential. Even if some of it is already realized, some of it is, but a great deal is just in potential, for addressing the fundamental issues which confront humanity today. And those are those related to human security and the security of the world we live in. And I think the mission of the Academy is really to look at solutions to global challenges. And we have spent much of our time in the last decades on focusing on the social solutions. But these research and recent other programs we've had really show the contribution that fundamental research in the natural sciences can make to creating a new world for us. So I thank you both for really
thank you, Gary. Thank you.
Patience. and Aleksander for taking this initiative and bringing us all together.
Thank you very much, Gary. The pleasure and the privilege was ours. We were inspired by
Gary.